All right, for college algebra 3.3, the zeros of a polynomial function. This will be part 1 of 2 videos for this lesson. Deciding whether x minus k is a factor of the function f of x. And before we do that, we're going to do a little bit of review. If I was to ask you, is 5 a factor of 12? Again, is 5 a factor of 12? Your answer would be no. But if I asked you, is 2 a factor of 12? Your answer would be yes. What you need to be thinking about if something is a factor of is if you were to divide by it, what is the remainder? See, if I took 12 and divide by 2, I have a remainder of 6. If I took 12 and divided by 5, I would have a remainder of 2. Therefore, their 5 was not a factor of. Well, this works the same for these polynomial functions. If I ask you if x plus 4 is a factor of this function right here, basically I'm asking you, if you took this x plus 4 equal to 0, you would have x equals negative 4. So if you were to substitute negative 4 into this function, would you get 0 for a remainder? Well, with synthetic division, I also had to realize here that I was missing an x to the third term. See, I have x to the fourth, x squared, the x term, and the constant. But I was missing x to the third. So notice the coefficients went 3x to the fourth, 0x to the third, negative 48x squared, 8x, and 32. You bring the 3 down, you multiply that with a negative 4, and then you add. You multiply that with a negative 4 again, and we add. 0 times negative 4, add the 8 plus 0, 8 times negative 4, and the remainder was 0. Since the remainder is 0, that would mean that x plus 4 is a factor of f of x. And the next question, I want to know if x plus 4 is a factor of this polynomial. So again, I would take the x plus 4, set the x plus 4 equal to 0. That would give me x equals negative 4 in the box. Make sure you're not missing any exponents. So as I look for those exponents, this is to the 5th, the 4th, the 3rd, the 2nd, the 1st, and x to the 0. So we're good to go. There was none missing. My remainder is negative 40. Now since the remainder is negative 40, that would leave me then as x plus 4 would not be a factor of the polynomial. So again, the remainder has to be 0 for it to be a factor of the polynomial. If the remainder is not 0, it is not a factor. Okay, part 2 of the lesson. I'm giving you the f of x is 6x to the third minus 37x squared plus 32x plus 15. And I want you to factor this into linear factors if 5 is a 0 of the function. Now, since I'm told that x equals 5 is a 0 of the function, I would start with x equals 5 over here for my synthetic division. Again, remember, to bring down the first coefficient, you always multiply and add and multiply and add. Got a remainder of 0, which I should. If 5 is a 0 of the function, that should give me a remainder of 0. Now what we need to realize in terms of the factor, if this says x equals 5, if I put this back equal to 0, that factor would be x minus 5. That's where this x minus 5 came from. Then, from the rest of this is the negative 3 is the constant term, negative 7x, and this is a 6x squared. That is where this came from. So again, there's the 6x squared minus 7x minus 3. You would then proceed to factor that using the concepts that were in chapter 1. If you do not know how to factor, please see me for notes on factoring. So you finish factoring that, and this would be your answer. Now, if the question had said to find the remaining zeros of the function, well, we already told that x equals 5 was one of the zeros. You would then take 2x minus 3 equal to 0, and you would get x to be 3 halves. 3x plus 1 equal to 0, and you get x is negative 1/3. So again, if the question said what was the remaining zeros, then your answers would be 3 halves and negative 1/3. If it said find all of the zeros, then you would include the original 5 in your answer. But it didn't say find all, it had said just find the remaining. Now this question actually had asked you just to factor it, so you would stop here. If it said to find the remaining zeros, this would be your answer, and if it was all the zeros, you would include 5. So what if they give me an imaginary root? It says for the following function, you're given one of the zeros is 1 minus I. Find the remaining zeros. And I'm given the polynomial function of x to the third minus 7x squared plus 12x minus 10. I want to make a note here that all of these coefficients happen to be real numbers. I got 1, negative 7, positive 12, and negative 10. Because these coefficients are all real numbers, and I have a complex imaginary root, I know that I have to have the conjugate as 1 as well. So I already know one of my other answers has to be 1 plus I. Now the degree is 3, so therefore I should have 3 answers total. We have 1 minus I, we know we should have 1 plus I as a 0, and we need to find one more 0. So we're going to start with synthetic division with 1 minus I in the box. So there's my 1 minus I. My coefficients, 1, -7, the 12, and the -10. Notice I was not missing any exponents. My first step would be to bring the 1 down. We take 1 times what's over here in the box. That would give me 1 minus I. When you add these together, you get -6 minus I. Now when you go to multiply these two right here, you're going to do your foiling or your boxing. Again, you're going to take -6 minus I times 1 minus I. You foil or box it out, it would give you -7 plus 5I. You add 12 plus -7 plus 5I, that's going to give you 5 plus 5I. Multiply 5 plus 5I with the 1 minus I. Again, foil or box, that would give you 10. When you add those together, you get 0. Now remember, see, they told you one of the zeros was 1 minus I, so that should give you a remainder of 0 for this to be a 0 of the function. Now we go ahead and we plug in the conjugate. So the conjugate would be 1 plus I. Now this one's a lot easier to do than the original. Everything will be nice and convenient, the i's will go away. So you bring down your 1 times 1 plus I would give me 1 plus I here. See, notice this time when I add these together, the negative I plus the I would be gone. Those would zero out. So -6 plus 1 would be -5. -5 times 1 plus I. So I distribute -5 minus 5I. When I combine those together, I get 0. So this ends up being x minus 5 equal to 0 to get my last root. Therefore, my remaining zeros are 1 plus I and x equals 5. If it said find all of the zeros, you would also list 1 minus I as an answer. What if the question had said, write this in factored form? See, if it said write it in factored form, we need to remember we had 3 roots. We had the original x equals 1 minus I from here. Then we had x equals the conjugate, that was the 1 plus I. And then we had x equals 5 as the last one. See, now if I put it back in factored form, that'd be like putting each one of those equal to 0. So I would subtract this 1 over here, so x minus 1, and I would add I over, because I want to make that equal to 0. So that would become x minus 1 plus I. The second factor, we would minus the 1 over, so there's the x minus 1. We would then minus the I over, and there's the x minus 1 minus I. On this one, we would subtract the 5 over, so x minus 5. So again, you got to really read your directions. Some of the questions in this homework and on my test are going to say just find the zeros, the remaining zeros. Some will say what's the answer in factored form. You need to make sure you put it like this. So are you finding the zeros or do you want the answer in factored form? Next example. Factor this into linear factors given that k is a 0 of the function. So right here at the end, it's telling me k is 3i. That means one of my answers is 3i. That's not one of the answers, I'm sorry, that's one of the zeros, one of the roots. Now notice this time I'm seeing a real coefficient of 1, but I see a complex imaginary one here, 7 minus 3i. This coefficient, 12 minus 21i, again, not real. -36i, again, not real. Because I have some non-real coefficients, I do not have to have the conjugate of 3i as a root this time. So I'm going to start with 3i in the box. My coefficient was 1. Coefficient was 7 minus 3i. Coefficient 12 minus 21i. The last coefficient, -36i. Now these actually work out pretty nice. When you bring down your 1 and you times up by the 3i, you get 3i. When you add this together, the i's are gone. Those zero out, you get 7. Take 7 times the 3i, so that's going to be 21i here. Add those together, the i's are gone, and you get 12. 12 times 3i would be 36i. Add those together and you get 0. So again, we want to write this all in factors. So since this said x equals 3i, I move it back over equal to 0. That factor would be x minus 3i. So again, x equals 3i, you move it over equal to 0. That's how I got x minus 3i. This is a constant term. This would be the x term. This is x squared. That's where I got x squared plus 7x plus 12. And again, back in chapter 1, we learned how to factor this right here. Most of you use the x factor in my classroom. So I'm looking for the factors of 12 with the sum of 7. If you do it to the x, that would be 3 and 4. You would have this as your factors then. Now, this question only said factor it, so that would be your final answer. If the question had said to find the remaining zeros, then you would have x equals -3 from this factor, x equals -4 from this third factor. Those would be your remaining zeros. All right, find the zeros of each and state their multiplicities. So the zeros of each means to take each factor equal to 0. So this first factor would be x plus 4 equals 0. Well, x would equal -4. This factor is x minus 6. Take it equal to 0 as well. So x minus 6 equals 0 would give me x equals 6. Now, the multiplicity is referring to how many times was it a factor of it? How many times does it count as a 0 of it? See, for example here, this x plus 4, that's raised to the 4th power. So this is going to be the 0 will be x equals -4, but with the multiplicity of 4. Okay, we count that root as 4 of them. This one would be x equals 6, but only to the 1st power, so therefore just x equals 6 with the multiplicity of 1. So again, the exponent to the binomial square like this, okay, that exponent is going to be your multiplicity. It's almost like that's how many times you count that as a root. Now that multiplicity is going to be important later when we get ready to do graphs. It's going to talk about where does the graph touch it or does the graph cross it. Those are the things we're going to talk about later in this chapter. All right, so find the zeros of this function given -2 is a 0 of it with the multiplicity of 2. See, that means x equals -2, but twice. That means the factor, if I have x equals -2, the factor would be x plus 2 times another x plus 2. That's where the multiplicity of 2 came in. That's why I do it twice. So we're going to start with x equals -2 in the box. Now I got to check for missing exponents to the 4th, to the 3rd, to the 2nd, to the 1st, nothing. So therefore, it was perfect, ready to go. Remember, bring it down, you multiply, add, you multiply, add, you multiply, add. Okay, got 0 as I should. Now, because it says a multiplicity of 2, you do this again. So we do -2 again. Again, we bring it down, you multiply, add, and so forth. So this one is x equals -2. This one is x equals -2. From here, I'm going to have, that's the constant term, -1x and 1x squared. So I'm going to have x squared minus x minus 30. Okay, everybody take a look at that. That was x squared minus x minus 30. From over here, we had x equals -2. So the factor was x plus 2. There was 2 of them, so that had a multiplicity of 2 right there. All right, so we already have the first factor. We already have that 0. I'm supposed to find the zeros, so I need to go ahead and finish factoring this. Could do quadratic formula, could do complete the square. Partially, I would factor it because there are factors of 30 with a difference of 1 of 5 and 6. So therefore, this 0 is x equals 6. This 0 would be x equals -5. If the question said to factor the problem, then that line would be your answer. The question said find the remaining zeros, find these zeros. So these are the remaining zeros. If it wanted me to find all the zeros, then I would include the -2 in that answer. All right, Descartes' rule of signs. This is something that's brand new to you from college algebra. This was not covered in your Algebra 2 class last year. So determine the possible number of positive and negative real zeros and the non-real complex zeros of a function. So the first one for the positives, you will not change any of these signs. You will write down each of those signs as you see them. So this is a negative here, negative coefficient, +4, -1. So again, just writing down the signs. I then need to count how many times does the sign change. So I see a change here and one here. There was 2 changes. Now what we need to realize is these are all real coefficients. When you have real coefficients, if you get an imaginary root, you must have the complex also. I'm sorry, the conjugate root as well. So if I have an imaginary root and I have its conjugate, that would mean they appear in two. They appear in pairs. They appear 2 at a time. So what happens then is how many ever you start with. So if I start with 2 positive roots, I also have to subtract 2 from that and say there could be 0 positive real zeros also. Now, I use the word roots and zeros interchangeably here. I prefer to call these roots. Our book prefers to call them zeros. Like I said, I'll just interchange those words. All right, so the number of negative zeros or negative roots. What you'll do for the negative roots is you're going to plug in a negative x for each x this time. I now need to figure out what their signs are. See, a negative x to the 4th power would be positive x, but then that's times negative 2. So that's where this negative came from. Again, that was negative x to the 4th power. Please excuse my dear Aunt Sally. You do your exponent first before you multiply. So the negative x to the 4th is positive, times negative 2 gives me a negative value. Negative to a 3rd power would be negative, but times that negative 3, that's where I got the positive. This time I have negative x squared, which would be positive, but that's times negative 5, so that is negative. 4 times negative would be negative, and that 1 is already negative. Now again, we want to count the sign changes. So there was 1, 2 of them. Again, take away 2 at a time because those complex imaginary roots are going to appear in conjugate pairs. So therefore, I had 2 of them or 0. Now, for the number of imaginary roots, what we will look at is, first off, I could have had 2 positive with 2 negative roots. That's what this first line is going to represent here. And now I need to figure out how many imaginary roots, non-real roots, I could have then. See, back here at the beginning, the degree is 4. So that means I should have a total of 4 roots. So if I have 2 positive and 2 negative roots, that would be a total of 4 roots. So therefore, there would be 0 complex roots there. If I have 2 positive roots, 0 negative roots, and right now it's only a total of 2 roots, I'd have to have 2 imaginary, 2 complex non-real roots. If I have no positives and 2 negative roots, that's only a total of 2 roots there. I'm supposed to have 4 total, so that would give me 2 non-real. If I have no positives and no negative roots, therefore then I would have to have 4 imaginary roots. So therefore, I'd either have 0, 2, or 4 non-real complex roots. Now I have a second example of this because this is brand new to y'all and you tend to struggle with it a little bit. So let's go ahead and do one more example of it. So remember, the number of possible positive real zeros. You don't change anything, just keep all your signs the way they are. Okay, do make sure this is in descending order though of the exponents. So that's the negative. This was positive 3. There's the negative from the 5. 4 was positive, 1 was negative. You count the sign changes. So it changes 1, 2, 3, 4 times. So there will be 4 positive real zeros. Or, now if I have 4, I then have to take away 2 at a time. So I take away 2, that gives me 2 or 0. So 4, 2, or 0. At this point, students usually ask me, well, what if there was 5? Okay, so if there was 5, then I take away 2, that's going to give me 3. Take away 2, it's going to give me 1. So if I started with 5, then my answer would have been 5, 3, or 1. So again, you take away 2 at a time till you either stop at 0 or 1. All right, the number of negative real zeros, you will plug in a negative x for each of the x's. So a negative to the 4th power would be positive, but times negative 2 would be a negative number. All right, negative x to the 3rd power would be negative, but times positive 3 is negative. A negative squared is going to be positive x times negative 5, that's negative. 4 times negative x would be negative 4, and the 1 is negative. See, there are no changes here. So there will be 0 negative roots. Now, do you see why I like to say the word roots here instead of zeros? I just think it gets a little confusing when I say there are 0 negative zeros. There are 0 negative roots. I like that better. All right, so my number of positive roots, there was either 4, 2, or 0. My number of negative roots was only 0. See, the degree of the polynomial is 4, so I know I should have 4 total roots. So, in this first case, 4 positives, 0 negatives, that's already a total of 4. That would leave me with no complex roots there. Okay, the complex non-real. If I have 2 positives, 0 negative roots, that's a total of 2, I need a total of 4. So that would give me 2 imaginary non-real complex roots. If I have 0 positives and 0 negatives, I'm supposed to have a total of 4. That would give me 4 non-real imaginary complex roots. So therefore there's 0, 2, or 4 non-real complex roots possible. At this point, we pause the notes. This will finish up our 3.3 Part 1. So for tonight's homework, please do these problems right here that are listed. I've given you a hint on number 11 that you'll need to use quadratic formula or complete in the square to finish it. Number 25 was the only Descartes problem. Because that was not enough for you to actually learn the concept, I have made an additional 3.3 homework. I cannot change the homework from the college. I can just add on homework assignments. So I have added on a homework assignment. You have 2 assignments for 3.3. One of them for Descartes' rule, the other one, which was assigned by the college. Do these problems tonight. Tomorrow we will pick up on 3.3 Part 2. Thank you and have a good night.